Welcome back, everyone. Today, we're going to be taking a deep dive into some really cool research about how large language models, those LLMs everyone's talking about, can actually tap into information on the internet, like in real time.
Yeah, it's a pretty big deal because it tackles one of the big limitations of a technique you might have heard of, retrieval augmented generation.
RSG, right.
Exactly, RG.
So what's the issue with RG?
Well, think about it this way. With standard ARG, an LLM is using a separate database, right, to try to find info that's relevant to what the user is asking.
Right, so it's like a digital library of sorts.
Yeah, you got it. But here's the thing. That database can get outdated super quick because, well, the internet's always changing. The research we're looking at, it's called Zero Indexing Internet Search Augmented Generation for Large Language Models. And it basically proposes a way to bypass that problem entirely by letting LLMs go straight to the source, the internet itself.
That sounds like a game changer. So is this just like a theory, or did they actually, make it work?
Oh, they built it, which is actually pretty awesome. The authors actually implemented it in a real system, so it's not just some pie-in-the-sky idea. You can see this in the Zero Indexing Internet Search Augmented Generation section.
Wow, so they actually built a working system. That's impressive.
It is, and they do a really good job of visually explaining the difference between standard ARGI and their Internet Search Augmented Generation approach. Take a look at Figure 1 in the paper.
Okay, so on the left side of Figure 1, we've got standard ARGI, where the LLM is stuck with that pre-built database.
Yeah.
And on the right side, with Internet Search Augmented Generation, it can search the web in real time. Huge difference.
Exactly. But this new approach comes with its own set of challenges, right? Things the researchers had to figure out. First big one is making sure the search results actually match what the user wants. You can't just chuck random search terms at Google and hope for the best.
Yeah, that makes sense. You need to understand what the user's really asking and then figure out the right keywords. So how did they solve that?
Well, they came up with a specialized LLM. They call it the parser-LLM.
So the parser-LLM is like a keyword detective.
Yeah, kinda. Its job is to decipher the user's request and figure out the keywords that'll lead to the most relevant search results.
Okay, so how do they train the parser-LLM to do that?
So first, they use this technique called multitask learning. It's pretty cool, actually. Basically means the model is learning to do two things at the same time. They describe this in the training parser LLM subsection. It decides if an internet search is even necessary and extracts the keywords all in one go.
That's impressive, like multitasking on a whole other level.
Yeah, for sure. But there's more. They also train the parser LM to understand how important time is. Sometimes dates are super important for the search, and other times they can actually make the results worse. The parser LM learns when to pay attention to dates and when to ignore them.
That's clever because it stops the search from being too broad or too narrow. Does the parser-LM have any other tricks?
It does. It can handle searches in multiple languages, not just the language the user asked in. And get this, it can even deal with words it's never seen before, like some weird company name. It won't just crash when it hits a new word.
Wow, that's pretty sophisticated. So they figured out the keyword problem. But what about the search results themselves? We all know search results can be a mess. How do they make sure they're getting the best information, not just the most popular stuff?
Great question. That's actually the second big challenge. Even with the perfect keywords, search engine results can be skewed by popularity. To address this, they use a mixed ranking strategy.
Mixed ranking strategy. Okay, what does that mean?
So it's kind of like a two-step process. First, they use the search engine's snippet, that short summary you see in the results, to get a basic idea if the page is relevant.
Right, that gives you a general sense of what's on the page.
Exactly. But they don't just stop there. They go deeper and analyze the full content of the web page too. This gives them a much more complete picture of whether it's actually a good match for the user's request. By looking at both the snippet and the full content, they can reorder those search results based on how relevant they actually are.
It's like getting a second opinion to double check you're not missing anything.
Yeah, good analogy.
Yeah.
So now they've tackled the keyword challenge and the ranking challenge. That means they have a bunch of web pages that are likely relevant to what the user wants, but they're not done yet.
Right, because web pages can be super long and complicated. How do they pinpoint the exact info on those pages, the stuff that actually answers the question?
That's where their next step comes in. It involves another specialized LLM, this one called the extractor-LLM.
Okay, so the extractor-LLM is like an information miner. It goes through those web pages and finds the gold nuggets.
Exactly. It's been trained specifically to spot and pull out the most relevant info from those web pages. They do something interesting here with pre-processing, using tags to break down the content on the page.
Tags. What do you mean by tags?
So they actually mark up the web page content with different tags, to show things like headings, paragraphs, lists, and stuff like that. Figure 2 shows an example of this.
I see. So instead of just throwing the whole web page at the extractor LLM, they're breaking it down into smaller, easier to manage pieces.
Exactly. This makes it much easier for the extractor LLM to do its job because it can zero in on the parts of the page that are more likely to have the important info.
That's smart. So the extractor LLM has a kind of roadmap of the web page.
Yeah.
But how does it actually learn to identify the right information, the stuff that matters?
Well, they have this two-phase training strategy for the extractor LLM.
2 phases. Tell me more about that.
All right, the first phase is called supervised fine-tuning, or SFT for short. This is where they basically teach the extractor LLM the basics of how to spot relevant content using those tags we were talking about.
So it's like they're giving it a set of rules to follow.
You could say that, but it's not just about blindly following rules. They actually want the model to understand why some text is relevant, not just that it is relevant. That's where the second phase of training comes in. It's called direct preference optimization, or DPO.
Okay, DPO. How does that work?
This is where it gets really interesting. They actually use another LLM, in this case GPT-4o, to act as a judge. So GPT-4o looks at what the extractor LLM is doing and gives it feedback, guiding it toward extracting information that matches what humans would consider good.
So it's like having a teacher that constantly helps the extractor LLM get better and better at picking out the most relevant information.
Exactly. It's a feedback loop that helps refine the model's performance over time.
I'm really curious to know if all this actually works in practice.
Well, that's what we'll be talking about in part 2. So you want to know if it actually works. Well, the researchers, they definitely put their zero indexing system through its paces. They really wanted to see how it stacked up against the traditional RAG systems.
Okay, so a head-to-head between the two approaches. What happened? Who won?
Well, if we take a look at Table 1, it's in the experiment section, it shows how well different LLMs do using both zero indexing and standard RAG, end-to-end performance. And what they found was that the zero indexing method consistently delivered better quality responses across all the different LLMs they tested.
So basically, zero indexing wins when it comes to the quality of the answers it gives. That's pretty cool.
Yeah, it is. And it wasn't just about quality either. Table 2 shows that the zero indexing method was actually using fewer input tokens, which basically means it's processing less data to get those answers.
This is more efficient too. That's awesome. Like a double win.
Exactly. More efficient means it can potentially generate those responses faster and even cheaper.
That's great news for anyone who wants to use these LLMs in like real-world applications.
For sure. But we can't forget about the extractor LLM, right? Gotta make sure it's doing its job right. So they tested it on 3 different benchmarks to see how well it could actually extract the correct information.
Okay, let's break down those benchmarks. What was the first one?
First one was a synthetic benchmark. You can find the details in the extractor evaluation section and Table 3. They basically created this benchmark specifically to see how well the extractor LLM could find really specific pieces of information, like trying to find a needle in a haystack. They even called those pieces of information needles.
So they hid these needles in different lengths of text and checked if the extractor LLM could find them.
Yep, that's exactly it. And the results were pretty encouraging. It did really well, showed it could pinpoint the right information, even when it was buried deep within a document.
So it aced the needle in the haystack test.
Nice. What about the second benchmark? All right, second benchmark was the open source benchmark described in Table 4. This one used real-world data sets to evaluate the extractor LLM on tougher tasks, more complex stuff.
What kind of tasks are we talking about here? Give me some examples.
Think multi-hop reasoning, like having to connect information from multiple sources to figure out the answer, or multi-answer retrieval, which means finding multiple correct answers to a single question, not just one.
So it's not just about finding one piece of info. It has to understand how different pieces fit together and maybe even find multiple answers.
Right, and guess what? The extractor LLM did awesome in these tasks, even outperforming GPT-4o in some cases.
Wow, that's saying something. Sounds like the extractor LLM, a pretty powerful tool.
It is. But the ultimate test, the one that really mattered, was the real-world benchmark. This one used actual user requests, like real questions people might ask, to see how the extractor LLM would perform in a real-world setting. You can see the results in Table 5, and let me tell you, the extractor LLM continued to impress, getting high scores across all the metrics.
So it's not just a theory. It actually works when you put it to the test.
Exactly. The researchers showed that their zero-indexing search augmented generation system is not just possible, it's actually really effective.
This has been super interesting, learning about how LLMs can access internet info in real time. It seems like they thought of everything when they designed this system.
Yeah, they put a ton of work into it, that's for sure. They tackled the challenges in a really smart and comprehensive way.
It's clear that this research could have a big impact on how we use LLMs in the future.
Absolutely. It's a huge step toward creating LLMs that are smarter, more up to date, and ready to handle the complex tasks we throw at them. Now let's dig into some of the technical stuff about this system. One thing that stood out to me was how they trained the parser-LLM.
Yeah, I was wondering about that too. In the training parser LLM section, they mentioned something about multi-instruction following capability. What does that even mean?
Basically, they trained the parser-LLM to handle multiple instructions at the same time.
So, like multitasking, but for an LLM.
You got it. It has to figure out if it needs to do an internet search and find the right keywords all at once.
That's a lot to handle. How'd they do that?
They designed a special instruction template that even a smaller LLM like the parser-LLM could understand. This let them get really good results even without any prior examples, which they call zero-shot performance.
Interesting. So they made the model more efficient by making the instructions super clear. What other challenges did they run into when they were training the parser LLM?
Another tricky one was dealing with time information sensitivity. They had to teach the model when dates were super important for a search and when they might actually make things worse.
Yeah, that's a subtle but really important difference. How did they teach the model to figure that out?
They put specific instructions in the training data that helped the parser LLM learn to tell the difference between queries with positive and negative temporal dependencies. Basically, they taught it when time was a crucial factor and when it wasn't.
That's really clever. And they even went further and used GPT-4o to make even more training data, just to make sure the model could handle all those time-related nuances.
Yeah, they were super thorough. They wanted to be absolutely sure that the parser LLM could understand exactly what the user meant, including how important time was to the search.
So the parser LM is multilingual and time-aware. That's pretty impressive. Were there any other limitations they had to work around?
Yeah, one more. They had to deal with the limits of monolingual keyword extraction. They realized that just relying on keywords from the language the user asked in might not be enough, especially for more complex queries.
So someone could ask a question in English, but the best keywords might actually be in a different language.
Exactly. So to fix that, they included instructions in multiple languages in the training data so the parser LLM could actually extract keywords from different languages.
That's a smart way to make sure they're catching all the important keywords no matter what language they're in.
Right. And then the last thing they had to deal with was out-of-vocabulary errors.
Out of vocabulary errors. What are those?
It's what happens when the parser LLM encounters a word it's never seen before, like maybe some obscure company name or a super technical term.
So it hits a wall because it doesn't understand the word.
Exactly. And they had a really cool solution for this. They actually trained the parser LLM on synthetic data that included made-up words.
Made up words. Seriously, how does that help?
By giving the model these pseudo words, they were basically teaching it how to deal with unknown words in a graceful way.
That's a really creative approach. It's like giving it a crash course in handling the unexpected. So now we've got a parser LM that can extract keywords from multiple languages, understands when time matters, and can even deal with words it's never seen before. What happens next in the process?
Next step is ranking the search results. Got to make sure the LLM is getting the most relevant information.
Right. We talked about their mixed ranking strategy before.
Yeah.
Remind me how that works again.
Sure thing. So they use both the search engine's snippet, that short summary, and the full content of the web page to decide how relevant it is.
Snippet gives you the quick overview, and the full content lets you dig deeper, like getting a second opinion from a more thorough source.
You got it. This helps avoid the biases that can happen with normal search results, where popularity can sometimes trump actual relevance.
Yeah, that's important because we want the LLM to focus on the most informative sources, not just the ones that are the most popular. They use an open source model called BGEM3 to help with the ranking, right?
Yep. BGEM3 plays a key role in figuring out how relevant the search results are based on those keywords.
Okay, so now we've got a set of the most relevant web pages. Time to get down to business and extract the good stuff, the actual information that answers the user's question. That's where the extractor LLM comes in, right?
Right on. The extractor LLM takes those web pages, which could be super long and complicated, and boils them down to the essential info.
And to make that easier, they use tags to break down the web page content into smaller chunks.
Yeah, remember figure 2. It shows how they use those tags to segment the content, makes it way easier for the extractor LLM to find the right sections.
Right, it's like giving the extractor LLM a map of the web page.
Exactly. The training for the extractor LLM is actually pretty fascinating. They use 2 phases.
Oh yeah, this sounds familiar. Tell me more about those 2 phases.
Okay, so phase 1 is supervised fine-tuning, or SFT. This is where they teach the model the basics of identifying relevant content using those tags we talked about.
So kind of like teaching it the basic rules of the game.
Yeah, you could say that. But it needs to go beyond just following the rules. It needs to actually understand why something is relevant, not just that it is. And that's where the second phase comes in, direct preference optimization, or DPO.
DPO, right. What happens in that phase?
This is where it gets really cool. They use GPT-4o as a judge. So GPT-4o looks at what the extractor LLM is doing and gives it feedback, steering it towards choices that align with what humans would prefer.
So it's like a mentor that helps the extractor LLM refine its judgment and really understand what makes information valuable and relevant.
Exactly. And they were super meticulous about how they set up this whole DPO process. They designed the judging instructions carefully, made sure the training data was good, and even did multiple evaluations to minimize bias and ensure the feedback was solid.
Sounds like they went above and beyond to make sure the extractor LLM was as accurate and effective as possible. Now, they evaluated the extractor LLM's performance using 3 benchmarks, right?
They did. They wanted to see how well it would do in different situations. The first benchmark, the synthetic benchmark, tested its ability to retrieve very specific sentences, those needles we talked about, hidden within different lengths of text.
So a very controlled test of how well it could find specific info within a larger context.
Exactly. And the extractor LM did really well. It got great scores across different categories like multi-hop reasoning, multi-question retrieval, and multi-answer retrieval.
So it can find the needle in a haystack,
Mm-hmm.
and it can figure out complex relationships between different pieces of information.
That's amazing.
What about the second benchmark?
The open source benchmark used data sets that were specifically made to test different retrieval abilities. It gave a more realistic picture of how the model would perform in the real world.
So it tested its ability to find info that's embedded in a more complex and nuanced context, like what it would encounter in real life.
Exactly. And once again, the extractor LLM did really well, even outperforming GPT-4o on some of the tasks. It showed that it could handle complex reasoning and multiple answers with no problem.
Wow, that's seriously impressive. So it can find the needle in a haystack, and it can understand complex relationships between information. What about the final benchmark?
The real-world benchmark used actual user requests, real questions people might ask, to see how the model would perform in a truly authentic setting. And if you look at Table 5, you can see that the extractor LLM continued to shine. It got amazing scores across all the metrics they used, things like precision, recall, F1 score, and exact match ratio.
It even beat GPT-4o when it came to precision and accuracy. That really shows how effective their training and fine-tuning process was.
Absolutely. It proves that this system isn't just some theoretical idea. It's something that can be built and used in real-world situations with great results.
It's kind of mind-blowing to think about how this tech could change how we interact with information, you know?
Yeah, it really is like a whole new way of thinking about things. Imagine like all the knowledge on the internet right there at your fingertips.
It'd be like having your own personal research assistant that could find anything instantly.
Exactly. And it's not even just about finding the information, it's about being able to make sense of it all, to really understand it.
The researchers also talk about how important it was to evaluate the extractor LLM, make sure it was working right. That's in the extractor evaluation section. Can you tell me a bit more about how they did that?
Sure. They used a bunch of different methods, testing the extractor LLM on a variety of tasks to see how accurate and efficient it was. One of the key things they looked at was the F1 score, which measures the balance between precision and recall.
So it's like making sure the model can find the relevant stuff without picking up too much irrelevant info.
Exactly. They also looked at other metrics like the exact match ratio, which tells you how often the model's extracted text perfectly matches the ground truth, the actual correct answer.
Sounds like a pretty thorough evaluation. Did they compare the extractor LLM to any other models?
They did. They compared it to GPT-4o, which is a really advanced language model that's known for understanding and generating human-like text. It's one of the best out there.
And how did the extractor LLM do against GPT-4o?
Well, it actually outperformed GPT-4o on some tasks, especially when it came to accurately pinpointing and extracting the most relevant information.
That's impressive. Seems like that specialized training they did for the extractor LLM really paid off.
Yeah, it did. They created a model that was specifically designed for this job, information extraction, and the results speak for themselves.
Yeah, we've been talking about all these different LLMs working together, each with its own specific role. Can you remind me what those roles are and how it all fits together?
Of course. So you start with the parser-LLM. That's the one that analyzes the user's request and figures out the right keywords to search for.
Like the first step, making sure the system understands what the user wants.
Right. Then they use that mixed ranking strategy, remember? That combines the search engine snippet with the full web page content to choose the most relevant search results.
Which makes sure the system is focusing on sources that are actually informative, not just the popular ones.
Exactly. And then once they've got those relevant web pages, the extractor LLM comes in.
And the extractor LLM is the one that goes through those pages and pulls out the specific info that answers the user's question.
Yep, that's the last step. It makes sure the user gets the most relevant and accurate info possible.
This whole system seems pretty complex. Did the researchers talk about any potential problems or areas for future research? They have a section called Discussion and Future Work.
They did. They pointed out that the system really depends on the quality of the search engine results. If the search engine doesn't find good pages, the system won't be able to give good answers.
Right, the system's only as good as the search engine it's using.
Exactly. They also said that more research is needed on how to evaluate how trustworthy different web sources are. I mean, we all know not everything on the internet is true or accurate.
That's a really important point, especially as these LLMs become more common in our lives. We have to be able to trust the info they're giving us.
I agree. Another area for future research is figuring out how to handle really complex or ambiguous queries. The current system does a good job with straightforward questions, but it might struggle with requests that are more nuanced or open-ended.
Makes sense. Like any new tech, there's always room for improvement. But overall, this research shows a really promising way to make LLMs even better.
Yeah, it's a big step forward in making LLMs more informed, adaptable, and able to handle the kind of information needs we have in the real world.
It's been awesome diving into the world of zero-indexing internet search augmented generation. Learned a lot today.
Me too. The way they design and train these specialized LLMs is really innovative. Definitely a lot of potential here.
I think our listeners will get a lot out of this deep dive. It's a topic that's going to shape the future of AI, for sure.
Couldn't agree more. This research opens up so many new possibilities for how we use information and knowledge. It's like we're on the verge of a future where LLMs can really be our partners in understanding the world.
That's a great point to wrap things up. Thanks for joining me on this deep dive, and to everyone listening, until next time, keep exploring the amazing world of AI.